So let me start first with Professor Hui-Ming Cheng. Professor Hui-Ming Cheng is a professor and a founding director of both Advanced Carbon Research Division and Shenyang National Laboratory for Material Science, IMR, KAIST since 2001, and the Low Dimensional Materials and Device Laboratory of the Tsinghua Berkeley Chen Institute, Tsinghua University since 2016. He has published over 700 papers with an H-index of 130 and is a highly cited researcher in both chemistry and material science field. He is the founding editor-in-chief of Energy Storage Materials and associate editor of Science China Materials. Without further ado, please join me in welcoming Professor Chen.
Okay, can you see my slides?
Yes,
hello.
we can.
Okay, good. So good morning and good evening, everyone. First, I would like to thank Hui-Ming and also Professor Kim for inviting me to give this talk. It is nice to have this talk after so long shutdown. So I'm Hui-Ming Cheng from China. So today I will give a very different talks from my previous talk. So I will present a kind of new consideration about the six-member ring in organic materials. So as you know, for this half years, we couldn't have time to do experiment and also to go around the world for attending conference. Therefore, we have more time to think. So today is some consideration about this thinking. So I hope my presentation can be some kind of inspiration for exploring the new six-membered ring in organic materials. So I will give my talk in this 5 parts. As we know, in organic world, the six-member ring, that means the benzene ring, actually is a start point. So back to 1864, the German scientist has discovered the structure of the benzene ring molecules. About these molecules, scientists have a comprehensive understanding. Therefore, we can precisely design and control the structures and functions of the organic molecules, such as we can synthesize phenol, benzoyl acid, and also many derivatives from those small molecules. So therefore, we can have a wide range of materials such as resin, synthetic fibers, paints, rubbers, and also drugs like aspirin and so on. However, in organic materials, basically we can classify into 2 groups. One is the structural materials. There are a variety of structural materials, including steels, superalloys, and titanium, aluminum, magnesium, and copper, and so on. And also we can make a wide range of structural materials by using multi-component solution allowing. In particular, when we develop those structural materials, we basically use phase diagrams, such as this one is iron carbon phase diagram, which plays an important role in developing mechanical materials, in particular, different types of steels. However, today, actually, it is very difficult to find a similar binary alloy system like iron carbon system. And we found that in those metallic material, it seems that we need a common structural factor to describe and connect various different structural materials, like I just said in organic materials. Another large group of inorganic materials is functional materials. We know that functional materials can have many properties such as magnetic properties, superconductivity, catalytic properties, semiconductivity, photoconductivity, biomedical properties, and so on, which can be used for energy storage and conversion, information, healthcare, and so on. So we know that the use of those functional materials have pushed the rapid development of information technology. However, similar to mechanical material, there is also a lack of a common structural factor that can link different functional materials. Okay, here, let me compare the organic materials and inorganic materials again. So from the classification, we have functional material, structural material, and composite material for both organic and inorganic materials. They almost have similar properties and applications. However, we found that a very big significant difference is their structure universality. So for example, as I just mentioned, for organic material, we have a structure universality that is carbon-based and 6-member rings for the organic small molecules, or macromolecules, or even polymers. So can we find the structure universality for inorganic materials? Right now, we don't have this. Does it exist? So then, let's say the 6-member ring in nature. We know that the 6-member rings actually is widely existed and also have very good stability and a high symmetry. For example, the honeycomb is a representative 6-member ring structure, which is very popular in nature. And also the structure of 6-member rings exhibit very good stability, not only for lattice structures, but also for microstructures. And then we found that a 6-member ring normally consists of 6 nodes, forming a closed ring with C3 or C6 rotational symmetry. And also in mathematics, actually, Euler demonstrated the Sixmember ring is the most stable, most ideal, and because the Sixmember ring structure actually pushed the frontier of science. For example, sorry, yeah, can you hear me? Okay. For example, so a scientist has discovered different types of molecules, drugs, and structures. And those structures have highly recognized by scientific world. Graphene is an ideal six-member ring structure which has many unique properties, as we already know. In fact, many other two-dimensional materials have a basic six-member ring unit. For example, germanium and molybdenum disulfide and bismuth selenide and even molybdenum silicon nitride or new material we found. And in the three-dimensional material, in organic materials, we also found six-member rings is a basic structure unit for many bulk materials like magnesium, barium, boron nitride, and even magnesium boride superconductors, and sodium bismuth, and the catalytic cobalt tin sulfide, and so on. So therefore, it seems that there are many materials with a basic six-member ring structure unit. And many of them actually have like graphene, molybdenum disulfide, boron nitride, magnesium boride have already become stars in their own fields. But we think quite little attention has been paid to the fundamental rules of the six-member ring structure unit among them. So as I show you here, there are many types of materials with SMR structure, which need more exploration. So therefore, we try to define the six-member ring materials. So basically, we focused on inorganic materials. So we think six-member ring materials should have a six-member ring structure layer as a basic unit with a three-fold or six-fold rotational symmetry. And the back form of this SMR materials is constructed by six-member ring structured layers bonded together by van der Waals, ionic, metallic, or covalent bonds, or with other atomic layers in two-dimensional or three-dimensional lattice. Okay, so now I'll change into the types of six-member ring materials. First, let's say there's structure and symmetry. So for both two-dimensional or three-dimensional SMR materials, the occurrence of SMRs is usually associated with a C3 or C6 rotational symmetry. And because of this structure characteristics, scientists has found the SMR materials in two-dimensional style or in three-dimensional style has some unique properties. For example, for two-dimensional materials, because of the structure unit, the material will have a Dirac cone, can be wide gap semiconductor, or have a spin valley coupling effect due to the pi bonding electrons or closed shell orbitals or spin orbital coupling splitting. And for three-dimensional materials, as I show you here, so also the material can be Dirac semi-metal or Dirac Nodal semi-metal or strand semi-metal, which can have negative magnetoresistance and anomalously large electron phonon coupling strengths and surface no travel topologically protected phonons. These are very unique physical phenomena and properties. And very recently, this group has found that a new material, three-dimensional material with SMR structure, cobalt tin sulfide, actually is an intrinsic ferromagnetic wire semi-metal, which has very unique property. They found that the anomalous Hall effect is very large, with very large Hall conductivity and also Hall angle. So an order of magnitude larger than all known typical magnetic materials and systems. So it's as you can see from the figure here. So the new material is very unique among other similar materials. So then let's see the common features of six-member ring materials. As I just mentioned, so the six-member ring material has a six-member ring structure. So this structure can consist of A1 and A2 atoms. And in some cases, can also have A3 atoms in the center. So these three atoms can be the same or different. And also the structure can be either flat or buckled off of the plane. And it is usually comprised of not only a single flat atomic layer, but sometimes also stacked atomic layer as well. So from the electronic structure, we can divide it into two groups. One is closed shell configuration, other one is no closed shell configuration. So for those two types, we can have insulator or semiconductor or semi-metal. And also, those materials show very different properties. We can have materials with very wide, very large band gap, and also can control the band gap, control the magnetic properties. For the non-closed shell electron shells, we can have Dirac nodal lines and magnetic wire phenomena, and even superconductors. And it's also we can have ultra high temperature thermoresistance and super catalytic properties. And this six-member ring actually can determine an interesting physics. So as I show you here, so this six-member ring structure can create a hexagonal Breuer zone, which uniquely determines the occurrence of the momental contrasting physics at the K and the K Planck point. So therefore, we can have different types of materials with very interesting physical phenomena, such as opposite spin splitting and opposite barrier curvatures, and the spins of Cooper pairs, and so on. And most interestingly, this six-member ring material can show interesting topological properties. So, for example, so this three-dimensional SMR materials with six symmetry. So the Dirac straight line states not only occurred along this direction, but also occurred along this direction. Therefore, they form this topological loader rings. So by breaking this rotation symmetry, this Dirac cones and the nodal lines and the nodal rings spin off into topological insulators, and wire framing metals, and wire nodal line states. Okay, so then I will change it to some possible applications. As we know that graphene is a typical six-member ring material which has wide potential applications in nanoelectronics, light modulators, sensors, displays, energy storage and conversion devices, and also painting and composites, and so on. So many groups are developing those applications into practice. Here, I just show you a few interesting possible application. The first one is the two-dimensional six-member ring materials may be used for topological field effect transistor, as this group showed. So the electric field actually can provide the driving force to switch on of the topological nature from this topological quantum spin Hall insulator. And also we can say that the three-dimensional six-member ring materials can be used for high-efficient water splitting. So as I show you here for this material, this is a molybdenum boride. So there are different types of molybdenum boride. So only this molybdenum diboride actually has a boron six-member ring structure layer. So we found that this molybdenum diboride actually has much better HER activity to the other three types of borates. These three types of borates do not have the boron six-member ring structure. So therefore, scientists have suggested this hexagonal boron diboride hosts topological Dirac rodal, you can see here, rodal lines, and the topological protected drumhead-like surface state, which may be beneficial to HER activity. Actually, not only those chemicals, and also some other chemicals with the six-member ring structures show higher catalytic activities as well. The third one is a work we have done, which just accepted by science 2 weeks ago. So we found that at this material, which also with has a six-member ring structure, has very high proton conductivity. It's 5 times higher than the niphon at a high temperature and high humidity, and over 10 times higher than the niphon at a low temperature and low humidity. As I show you here, this is the new material. This is the proton conductivity of niphon. So we measured this at very high humidity, 98%, and with the temperature increase, our material showed a high, increased conductivity. This is very interesting properties. Finally, I will go to the prospects. First, so we would like to consider where, how, and to find new six-member ring materials. So we think the new six-member ring materials may contain non-metal sp and metal sp electrons. So that's because 2 reasons. One is they easily form covalently bonded rings. The second is the metal and non-metal reactions are usually axiomatic, and which can provide enough energy for the formation of a covalent six-member ring structures. So for 2-dimensional SMR materials, we predicted, so we can find this SMR material from those combinations. So that's for low closed shell monolayer. So we can have different types of 2-dimensional materials for single element or for compounds. For the closed shell monolayers, we also predict the different and various combinations of 2 or even 3 components. For the similarly, for the 3-dimensional six-member ring materials, we also can have different types of combinations, as I show you here, MX or MX2, and M2X and M3X, and even 3 elements like MXP and so on. So there are quite many combinations. So we can calculate those structure, the stability of the structure, and try to synthesize the material, and then found their unique properties. The second is how to discover new six-membered ring materials. So we know that there are many van der Waals layered material. So over 5,600 compounds are those 3-dimensional layered material. So we can exfoliate from those material to get a new 2-dimensional material to measure their properties, as I show you here. However, more importantly, we need to predict the material by using the strategy combining computation and data-driven experimental strategy. So, as I show you, the six-member ring material can consist of 3 types of atoms. So then we can predict possible stable structures and compositions, and also predict their promising physical and chemical properties, and then to use the state-of-the-art experimental synthesis strategies to get those new six-member ring materials. So I will give you an example we have done. So we try to predict those 3 element family, metal, Ma2Z4. So we choose a metal from here, and another element like silicon, germanium from this family, and also to get nitrogen, phosphorus from this family to make this 3 element material. And we try to understand some unique feature of this material. For example, through the first principles calculation, we have predicted the material with spin valley coupling, and also ethane superconductivity, and topological insulation. So there's 3 types of materials. And also we have predicted that this material may have a series interesting magnetic properties, such as ferromagnetic spin gapless semiconductor and ferromagnetic half metallicity. So there's also 3 element compound. And we do synthesize this material. For example, we have synthesized this molybdenum silicon nitride. Actually, this material is the first synthetic 2-dimensional van der Waals layer material, because we cannot find a similar material in the nature of this material. No long 3-dimensional allotropes. So the synthesis is quite simple. Some years ago, we developed a CVD process based on 2 metal substrates. So here we use copper molybdenum substrate and ammonia gas and to supply nitrogen and source. Interestingly, if we don't use silicon, we can only get this non-layered molybdenum nitride, which is island on the substrate. However, if we add silicon, we can get a monolayer molybdenum silicon nitride, which show very nice polycrystalline and continuous thin film, as I show you here. The thickness is around 1 nanometer, which is exactly the same as we observed for 1 layer by the HRTM. And we found this structure actually is has 6 atomic layers: nitrogen layer, so nitrogen layer, and silicon layer, nitrogen layer, molybdenum layer, and then silicon layer, nitrogen, nitrogen layer, silicon layer, nitrogen layer. There's 6 atomic layers, and also has a 6-member ring structure. So this the high resolution and TM you can see here. So we can observe the silicon layer, molybdenum layer, silicon layer. Nitrogen layer is very difficult to be directly observed. and also by the element analysis, we have proved those structure. And also we found this material has very nice properties, which shows semiconductivity, semiconductivity, and also strong, very high use modulus in between the graphene and the other types 2D material like molybdenum disulfide. This is our material. Okay, so the finally, so which directions we need to focus on the six-member ring materials? We also have some consideration. As I show you, so from a physics part, we needed to consider their applications such as quantum computing and topological field effect transistors, spintronics, and spin winding coupling, and so on. So for mechanical consideration, we can use those six-member ring material as ultra high temperature ceramics, hypersonic aerospace vehicles, used in hypersonic aerospace vehicles, and so on. We also can use those materials as super lubricants, which has very weak spillage resistance. We also can use this from the chemistry point of view. We can use this as six-member ring material in corrosion resistance and protection field, and also energy conversion, such as hydrogen inversion and oxygen inversion in water splitting. So there are actually numerous six-member ring materials need to be explored. We don't know how many, and I'm sure there are many. And the following main aspects may be our initial steps. The first is the six-member ring materials can be very nice platforms to discover new physics, as I already showed you. Although I'm not an expert in those fields, so we can find many topological, ferromagnetical, and so on, those unique physical properties in the six-member ring materials. The second is for practical application, we can find new six-member ring materials as a high-performance catalyst for energy conversion. Actually, the energy, clean energy is very important. However, we still struggling for obtaining high efficiency catalyst. Platinum is good, but the platinum is not cost effective. So we need to find some new materials. We think the six-member ring materials may be a good target. The third one, because the six-member ring material actually basically have a strong covalent bonding. Therefore, many this material like zirconia boride, hafnium boride, and so on, have very good high temperature properties, and therefore this family of materials can be very good ultra high temperature ceramics. Now we are going to develop as well in our laboratory. Okay, so I raised a new consideration of six-member ring in organic materials. So I will summarize it. So a six-member ring structure layer as a basic unit with a 3 fold or 6 for the rotational symmetry. And the materials actually is a rich family with single elements or compounds. And also this material have very unique physical, chemical, and mechanical properties. So we think the use of those material may cause revolution in the fields of information, energy, space, and so on. So here again, I give you the figure I used. So there are many different types of six-member ring in organic materials. And those are already known, and many are unknown, actually, need a way to explore. So therefore, I think the six-member ring material deserve wide attention and in-depth investigation, from materials design, new physical discoveries, to target wizard applications. Okay, I would like to thank my collaborator. Actually, we discussed a lot with 5 people. So Professor Hui-Ming Cheng is a physicist. He working on prediction of new materials. So Gang Liu is working on energy conversion. Wen Cai is working on two-dimensional material. Bilu also is working on two-dimensional material. So in this science generally, we have quite a few group meetings and try to draw this concept and wrote a feature article for the National Science Review. And the work I mentioned in my presentation from our group has been done by these 2 PhD students. And this one is for the proton conductivity, the science paper. This one is for the new 3-element compound, molybdenum silicon nitride, our science paper by this student. I thank you very much for your kind attention, because this is a very new consideration. Maybe it's not correct. I need your feedback. You can send an email to me at any time. Thank you. Thank you very much.
Thank you very much for introducing the new research field. It's a very interesting and very impressive and wonderful presentation. Now time is open for question. Then please let me check the Q&A box, and I will read this question for you. Thank you for your talk. Could you clarify what makes the six-membering ring structure special compared to other geometry?
First, I think the six-member ring is the most stable structure. So, which makes the wide existence in materials and also in nature. The second is six-member ring structure has very high symmetry, so which brings very unique physical properties. I think there's 2 reasons maybe is very different from other structures.
Thank you. And second question, so do you have any helpful tips that you could share regarding the transition from computational prediction to experimental success? I would imagine certain compositions are difficult to synthesize. What are some techniques?
Okay, so that's a very good question. So actually, right now, because I think if we want to find this new six-member ring materials, we needed to a very strong collaboration between the computational science and the experimental synthesis. So right now, we are working on that. So I hope some new materials could be discovered by this way. Right now, I don't know exactly what is the effective way to do that. But really, as I said, at my laboratory, at my institute, Professor Hui-Ming Cheng is a very good physicist on prediction of new structures and new properties. So we are working together very closely. We discuss almost every week on new ideas, and also the theorists need to consider the possible synthesis way, and that's very important. And someone can only predict the new material, but they don't consider any possibility for synthesis. I think when we design the material, the possibility of synthesis should be considered in the beginning.
Okay, so last question. Thank you for your nice talk. Could you explain the concept of topological insulator and how to investigate and predict the physical property of that?
That's a very difficult question for me. Actually, topological insulator is a wide field, and physicists have done a lot on that. I'm not a physicist, so I cannot tell how to work on topological insulator. I'm so sorry.
Okay, so I would like to thank the Professor Chan for your precious time. Then let me move the second, the speaker, the Professor.
Okay, thank you very much.
Thank you.